Okay, so we'll continue from here. So earlier to this, we were discussing purpose of embedded systems, and these are the important purpose of the embedded system. So why embedded systems are used in so many application domains. So mainly for collecting the data, storing the data, and representing the data. And then for data communication, we use it for making the embedded system, one embedded system to share the data with the another embedded system, or for data exchanging or information exchanging. And embedded systems are also used for data processing, monitoring purpose. So when I say monitoring, you use a device for monitoring the status of the variables, current status of the variables. So majority of the devices which are available within the healthcare domain or medical domain, or the monitoring systems, and then the control systems are also there. Now using the monitoring system, we go for monitoring the state of the variable, and based on the current state of the variable, we go for updating or changing the states of the variable. That is what is control. And then application specific user interfaces. So we can go for using the embedded systems for building an application specific UI also, user interface also. So these are the main purposes of the embedded system. Now, I think this I've completed it. So collection, storage, or representation. So we can go for using the embedded system, either one single embedded systems or different embedded systems for collecting the data, storing the data, and representing the data in the human readable form. So and when I say data here, what is the data? Data can refer to any kind of information. Either it could be a simple textual information, so which is being collected and stored and represented, or it could be multimedia data such as voice, image, video, all these things. Okay, ultimately any measurable quantity can be collected using an embedded system, stored, and it can be represented in the human readable format also. So, okay, these are all the kinds of the information what an embedded system can receive and store. But again, the data, all this data, either it could be text, voice, image, all these things, they could be in the two format. One is analog format and other one is discrete format. So analog is nothing but the continuous format, and digital or the discrete format is nothing but storing the data in terms of zeros and ones. So now if an embedded system is designed to capture the data directly from an analog signal, it collects the data directly from the analog signal, and then for storage purpose, before storing the data, it should be converted into the digital form. And for that, we got to use an ADC, analog to digital converter, okay, which is going to convert the continuous data or the analog data into binary equivalent data. So all of you know everything is stored in terms of zeros and ones within the computer system or any system which is running a microprocessor or a microcontroller. Everything is stored in terms of zeros and ones. Ultimately, any analog data, either it could be a voice analog data, image analog data, or video analog data. So, and or it could be a simple electrical signal or any other form of signal. So, which is in the form of analog, or the continuous format should be stored in the discrete format, that is in terms of zeros and ones. And the ADC, analog to digital converter, plays an important role in doing this. And next, uh, and you can store directly in the system. The data collected can be, sometimes we can go for storing directly in the system, or sometimes we go for transmitting it from one system to the another system, or sometimes after processing and giving some meaningful representation to the data, we go for instantly deleting it. Okay, and these actions, whether you store it or you transmit it to the another embedded system, or you're going to delete it instantly after giving a meaningful representation to the data, is purely dependent on the purpose for which the embedded system is being designed. Okay, so not all the systems are going to do all these tasks. It is purely the dependent on the purpose for which the embedded system is designed. And here is the example for the embedded system which receives the data. Okay, receives the data, gives some meaningful representation to the data, and after that it is immediately deleted. Okay, immediately deleted. And next, what we have another example for the embedded system, which is going to collect the data, store the data, and even represent the data. Okay, so this digital camera is the best example for the embedded system, which is going to receive, store, and also what represent. So when you capture the photo or the image, so the embedded system is collecting the data or performing the data acquisition, and then after the data is acquired or the image is acquired, it goes for storing it inside the memory. Okay, storing also it is doing, and how it stores. So again, there is a completely big discussion on this. And then after storing, so whenever I want to view back my images, again you can go for accessing it. So it is going to access the data which is stored inside the memory and present the information to the user in the form which the user can view. Okay, so this is another example. So next is data communication. So apart from the purpose of receiving the data, storing the data, and representing the data in the form which is readable by the humans. So the embedded systems are also used for the purpose of data communication. And again, when I say data communication, it could range from the satellite communication system to simple home networking system. So that is what is the range of communication that is supported by the embedded systems these days. So from a simple home networking communication to the satellite communication is possible. Okay, and then what the data collected from one of the embedded terminal, so can go for transmitting it to the another embedded terminal, so located remotely. So located far away from the embedded terminal that is sending. And again, the transmission, it can be achieved either by using a wired means or a wireless means. Okay, so in the early days, all communication between the embedded systems used to happen through the wired means. Okay, so but these days the majority of the communication between the embedded systems is happening through the wireless means, because there are plenty of advantages using the wireless means of communication between the embedded system, because since I say the wireless medium, so it will make the communication links free from the hassles of the wire bundles. Okay, so this is on the data communication and what type of communication units are available. So the data collecting embedded terminal itself can incorporate the communication units. So it's not like the embedded system which is acquiring the data can only acquire and it cannot send the data to the other devices. So even the embedded system which is designed in order to collect the data can also be made to send the data to the other embedded systems. Only thing is it should the embedded system which is collecting the data should incorporate the data communication units like these things. These are all the wireless units. So are the wireless modules. So Bluetooth and few of these things you are already familiar with it. So who is not familiar with the Bluetooth? And you people are already using it. Zigbee, Wi-Fi, and you people are familiar with this also. Edge, GPRS, and most of the things that are already familiar. And these are the wireless modules what the embedded system uses in order to share the data with the other embedded device. Now, when it comes to the wireline modules, so we have these things, and these things also are already familiar, but only thing is you have seen, but you might not know. So that itself is RS-232C. Okay, and RS-485 is also there. So RS-232C cable and RS-485, and then USB, and all of you are familiar with this. And so I guess everyone of you has one device which is compatible with, so which has an USB port. So your laptops has USB port, your desktops has your USB ports. Okay, and even you can make your phone communicate with the laptop or the desktop through the USB cable. So TCP/IP, PS2. So these are all some of the examples for the wireline modules, and so appropriate pictures of them is also given. Okay. Yeah. Now here, if you look at, so the network hubs, routers, switches are also the typical examples for the dedicated data transmission uh, of within the embedded system. So what you're seeing here is a D-Link switch, which is an 8-port switch, so Wi-Fi module and a network hub. So these kind of devices are also available. And what these kind of devices are going to do is, so they act as a dedicated data transmission mediums, okay, from one to the other. Say I have one embedded system, another embedded system, say I just want to make them communicate. So they stand in between all these things, okay. And then they also provide the data security and the monitoring features. And this, I guess all of you know, this is the Bluetooth symbol and this is the Wi-Fi symbol. So next is data processing. So hope you people are following.
Yes, sir.
Yes, sir.
Okay. Okay. So data processing. Now again, okay, embedded systems are designed to collect the data, to store the data, represent the data, and also for transmitting the data from one embedded system to the another embedded system. So they don't do only these things. Even they also go for processing the data. So processing the voice, processing the image, video, electrical signals. Okay, all this data can be processed by the embedded system. Okay, so example, the best example that you can give for this is the digital hearing aid. Okay, so what digital hearing aid? It is again also a small embedded system which is going to improve the hearing capacity of hearing impaired person. Now, in order to improve the hearing capacity of the hearing impaired person, what it has to do, it has to receive the audio signals, and it should go for amplifying them. Okay, so you can just the small picture of that is also given. Okay, so you can see there is an amplifier and there is also a battery, a small battery, very small battery. Okay, and then there is a microphone. What this microphone is going to do, it's going to catch the audio signals, and the amplifier will amplify the signal, and then the speaker will play it for the user. Okay, so this is, and what it is doing, it is doing some kind of a data processing. Amplifying will not happen without the data processing. Okay, next is monitoring. So now and majority of the devices which are there in the healthcare domain come under this category, monitoring. So what they do, they are used for monitoring the state of some variable. So we determine the state of a variable and we keep monitoring that. Okay, and you can just say what is the state of the variable, that's all, but it is not possible for you to change the state of the variable. So that is what is monitoring. For example, very good examples for this are your ECG mission, electrocardiogram missions. So what they do, so they have the capability of only monitoring the heartbeat of the patient. Okay, and they cannot impose the control over the heartbeat. So what they can do, so they can just monitor. We have the sensors connected, so which are in the form of an electrodes to the patient's body. So they measure the current state of the heartbeat, and they are displayed on the display devices, but they don't have the capability to control. Okay, next. Other examples are also there. Plenty of examples you can give, and majority of the examples are again from the monitoring system. Oh, sorry, healthcare domain. So other examples are like digital CROs. So this is digital CRO is also the same thing, which is used for the purpose of monitoring, just for the purpose of monitoring. And then digital multimeters is also for the purpose of monitoring. Say I want to measure the voltage between 2 points. So I measure it. So either I can go for measuring the DC voltage or the AC voltage, current I can measure, resistance I can measure. So all these things, what I can do, I can go for measuring. That means I can determine the current state of the variable, but not possible to change that. And then logic analyzers are also there. So these are some of the examples for the embedded system which are designed with the intention of monitoring the state of some variables. But these things, they cannot impose the control over the variables. Next is control. So embedded systems with control functionalities impose control over some variables according to the changes in the input variables. Say they keep monitoring the state of the variable. So when certain limit is attained, so even this embedded systems which are designed with the intention of controlling the state of the variable can also go for changing the variable state. So they keep monitoring. So whenever some threshold is met or whenever some limit is reached, so this control the embedded systems which are designed with the intention of controlling will have the ability to change the state of the variable also. And majority of the embedded systems which are designed with the intention of controlling are connected with two components. One is the sensors. Now using the sensors, so this is what I've said. Systems with the control functionality contain both sensors as well as actuators. Now, what are sensors and where are they connected? So sensors are the devices which senses the data, okay, in the analog format and transmits them to the embedded system. What embedded system does, receives those data which is in the analog form sensed by the sensors using an ADC, converts the analog data into the digital data, and then goes for storing or processing all these things. Now, since sensors are sensing the data and sending it to the embedded system where they should be connected. So they're connected to the input port. Okay, sensors are connected to the input port of the embedded system. And where are the activators are connected? So activators are connected to the output port of the embedded system. Now what these activators are going to do, so whenever the sensor senses data, sends it to the embedded system, and embedded system is monitoring or processing, monitoring the state of the variable, and whenever certain limit is reached or threshold is reached, it'll go for sending the output to the output port. So and the output that is sent to the output port is goes to the activators, and these activators are going to control the functioning. So the state of the variable is changed, and that is sent as output to the activators which are connected to the output port of the embedded system, and these activators are going to control the other devices. Okay, so best example what we can give is the ACs. Okay, now what we have said, the room temperature, what I have set is 20 degrees Celsius. Now what, and the compressor of the air conditioning system will go on until the temperature of the room is bring down to 20 degrees Celsius. The moment the room temperature gets down to 20 degrees Celsius, what will happen? The state of the output variable is changed, and that goes to the activator. The moment the state, the change in the changed variable goes to the activator, so the compressor is turned off. So that variable will make the compressor go up, and the compressor will remain in the off state until the room temperature increases above the 20 degrees Celsius. When it increases above the 20 degrees Celsius, again, one more, the variable state is changed and the output is sent to the activator, and the activator now will go for turning on the compressor once again. So this is the example, and like this you can give plenty of examples. Okay, and see, an air conditioner contains a room temperature sensing element, and what is that? Thermistor is the one which is used for sensing the room temperature, and a handheld unit for setting up the desired temperature. What is an handheld unit is? That is your remote which we use in order to set the desired temperature. Next is application specific user interfaces. So this is another purpose of embedded system. So we go for using embedded systems for designing the buttons, switches, keypads. And these are, so this altogether is an embedded system, and within this keypad itself is one more embedded system, and this keypad is specifically designed for this embedded system. Okay, and within this keypad also you have a small microcontroller. Okay, so buttons, so switches, keypads, lights, speakers, display units. So these are all some of the examples for the application specific user interface. So the keypad which is designed for this particular embedded system, I cannot go and use it for some other embedded system. Okay, so like that. So mobile phone is an example for the application specific user interface. In mobile phones, the user display is provided through the keypad, and the display is provided through a graphics LCD module. Speakers are also there, and vibration a lot. So these are all some of the output devices for the handheld system. So these are some of the important purposes of the embedded system. Okay, so and lastly, so summarizing. So summaries are always important because summaries will give you an insight into the whole lot of things what we have studied in the last 3 to 4 classes. Okay, so initially what we did was understanding the definition of the system. So initially we understood the definition of the system. Now, what is a system? Can anyone define the system? What is a system? Sorry, your voice is breaking. I can't hear you. Hello.
A collection of interrelated systems for a specific task.
Very good. Very good. So system is defined as a collection of interrelated components, so which work together to achieve a common purpose or a goal. Okay, using the combination of embedded hardware and firmware. Okay, that is what is the general definition of the system. And then embedded system, we understood embedded system as either an electronic or electromechanical system, which is designed with the intention of performing a specific task. So, and after that, so we went through the IEEE definition of the embedded system also. So IEEE defines embedded system as a device that is lodged in other devices to control their functioning. And then we looked into the differences between the embedded systems and the general computing system. So I think we understood the differentiating characteristics between the embedded systems and the general computing system with respect to around 7 to 8 key factors. So based on the 7 to 8 important key factors, so we tried distinguishing the embedded systems from the general purpose computing system. And then we looked into the history of the modern embedded systems. Okay, so just like we people study the history of the computer generations, so similarly, so we went through a very brief history of the modern embedded systems, and then we looked into the classification of embedded system. So generally, embedded systems are classified from 4 major perspectives. One is classification based on the generation. So first classification is done based on the generation, and the second classification was done based on the complexity and what performance of the embedded system. And there were 2 other classifications also, but those 2 classifications are not there in the syllabus. So you have only the first 2 classification. So and we understood in detail the generation based classification, and then we understood in detail the classification of embedded system based on the complexity and performance. And then we also looked into the purposes of the embedded system, main purposes of the embedded system, and we had a detailed discussion on all the important purposes of the embedded system. And before that, we understood the application domains of the embedded system also. So we nearly understood around 11 application domains of the embedded system, starting from the consumer electronic devices to the last one. I think it was the last one, 11, around 11 application domains we understood. So card readers, okay, banking and retailing, measurements and instrumentation, healthcare, computer networking, computer peripheral. So these are all some of the application domains that we understood. And after that, so we looked into the purposes of the embedded system. So purpose of the embedded system for data collection, storage, representation, data communication, data processing, monitoring, control, and application specific user interface. Now this completes your first chapter in module 3. Okay, and now we'll get into the second chapter, chapter 2 of module 3. So again, the first chapter of module 3 was introduction to embedded system, but chapter 2 we focus more on the core of the embedded system. Okay, core components of the embedded system. Again, in the chapter 2, so these are the sections which will be studying. So even in the syllabus, so just 2.1 to 2.6, okay, you got to read. So 2.1 is understanding the core of the embedded system. In 2.2, we understand the memories of the embedded system. So we have already discussed the different types of memories used in the embedded system in the first module itself. So there we had a very brief discussion. So it was not an in-depth discussion. So but here we are going to have a complete and depth discussion on the different types of memories used within the embedded system. So there, when I was explaining the DRAM, so dynamic random access memory, so I said there is a disadvantage of DRAMs. Can you people recall that disadvantage? What is the disadvantage of DRAMs? So generally we call DRAMs are much slower. Now what makes DRAM slower? Hello? Please try to
We
recall.
have to refresh the memory once a while.
Yes. So refresh in the sense you got to keep supplying the new electrical charges in milliseconds range. Okay. So if this could not be done, so your DRAM will forget. Okay. So the data which is there inside the DRAM so will be lost. So the new electrical charges has to be supplied say in the milliseconds range. Okay. Now why it is so? Why it has to be supplied in the milliseconds range? Okay, that is what we look into the implementation part and we understand. And then so to overcome this disadvantage, next the static RAMs came. SRAM came. And SRAM, it is not necessary for you to keep supplying the electrical charges every milliseconds. It is not at all necessary. Why it is not necessary here? How the implementation of DRAM is different from the implementation of SRAM, or how the implementation of SRAM is different from the DRAM. So these are all the things which you are going to understand here. Okay. And after the memory, so this is just an example which I gave you just to make you how we are going to discuss the memories in depth. And next is sensors and actuators. So I've already mentioned in the previous slide. So when I was explaining the purpose of the embedded system, so controlling purpose of the embedded system. So we have sensors connected to the input ports of the embedded system mainly to read the data, and we have the actuators connected to the output ports of the embedded system. Now, when the embedded system processes the data and when it changes the state of the variable, the changed state of the variable is sent to the activators connected to the output port of the embedded system, and these actuators in turn based on the state of the variable will go for controlling the functioning of other mechanical devices which are connected to this. Okay, so other mechanical devices in the sense either it could be a relay. Say I was talking I was giving the example of the ASIS when I was explaining the embedded system for the which is designed for the purpose of controlling. I was giving the example of AC, air conditioners. So when the actuators which are connected to the output port of the AC receives the changed state variable, now what it is going to do? It is going to either turn on the relay or turn off the relay. If it turns on the relay, then the compressor is on and it is running. So if it turns off the relay, so then the compressor automatically goes off. What the actuator basically does is, so majority of the times they're connected to the relays, which are going to turn on or turn off the functioning of other devices. And then we will be looking in detail into the communication interfaces. Even in the previous slides, when I was explaining the embedded systems which are designed for the purpose of data communication, I mentioned a few wireless modules and few wired modules. Okay, so for wireless modules, I mentioned Bluetooth, Zigbee, Wi-Fi, Edge, GPRS and all these things. Now here in the section 2.4, we are going to have incomplete and detailed discussion on all these wireless modules. Okay, so not only wireless modules, so we also discuss in detail the wired modules also. So either RS-232C, RS-485, and then we have other things called as I2C bus, all these things. Okay, all these things we understand them in much depth, and then we understand the embedded firmwares. Okay, so we'll be discussing on the embedded firmwares. So how the firmwares are designed, what are the factors that you should consider while designing an embedded firmware, and then we also look into the other components of the embedded system. So it is not restricted only to these things: memory, sensors, actuators, communication interfaces, and the firmware. So we also discuss in brief the other components of the embedded system as well. Okay, next. On the learning objectives. Okay, now you're going to learn about all these things. Now we know that, so building block of, we learn the building block of the embedded system, and what are all the building blocks of the embedded system? These are all. So either it could be a general purpose processor, short form we call it as GPPs, general purpose processor, or an application specific instruction set processor, or a microprocessor, or a microcontroller, or a DSP processor, or it could be a RISC processor or a CISC processor. And again, either it could be based on the Harvard architecture or Von Neumann processor architecture, and big Indian and little Indian processors. So again, I even in the module 1 and 2, when we were doing the programs and when we were storing something on the processor, I used to say you got to read from the LSB position towards the MSB position. And on some architectures, you got to read the data from MSB position towards the LSB position, and that is basically because of the implementation. So the mission, some processors are implemented using the big Indian representation, and some are implemented using the little Indian representation. So where the processors which are implemented as little Indian representation, when you're reading the data, you have to start reading always from the LSB position, that is least significant byte position. Then you should proceed towards reading the bytes towards the most significant byte position. Okay, so that also we understand. And then load and store operations and instruction pipelining. So load and store. So we have understood even earlier also in module 1 and module 2. Now you know what is load operation is. Getting the data. What is load operation? Hello? What is load operation?
It loads the value from memory to register.
Very good. So load instruction you have understood, and not just one load instruction, simple load instruction. You understood a load instruction which loads one register at a time. Okay, and then we also understood that is LDR, and then we also understood what is the instruction that loads multiple memory locations to the multiple registers. What is that instruction is?
LDM.
LDM. Very good. So load multiple data. Okay, so loads the content of several memory locations into the multiple registers. Okay, and similarly store operation, which is going to transfer the content of one register into a memory location. Again, store also we have store a single memory location and store multiple memory location. So store multiple, what it does, it treats the content of multiple registers and then loads them into the different memory locations, stores them into the different memory location. So we also understand instruction pipelining, because store and load, so they create load interlock problem. Even this also we have understood when we were discussing the optimization techniques. Okay, how to optimize the ARM code. When we were discussing that topic, we have also understood the problem that is created by the load and store instruction. They create something called as what load and store interlock problem. Now, how to deal with all those things when the instructions are getting executed in a pipeline fashion. So these are all the things which we are going to understand. Okay, so And not only this, so we also understand the PLDs, programmable logic devices. So there are two such programmable logic devices. One is CPLDs, complex programmable logic devices, and FPGAs, field programmable gate arrays. So we are going to have a in detailed discussion on these two things later. So let us not worry about these things. So at this point of time, even you people don't know what is PLDs, programmable logic devices. So what are PLDs are nothing but, so the name itself is saying programmable logic devices. So you can go for programming these devices as per the logic which you need to implement. Okay, so there are two ways of doing it, by using the CPLDs and by using the FPGAs. And then see what I'm giving you is the insights into the things that we are going to learn in this chapter. Okay, so you are going to learn about the different memory technologies. So you understand, see here, so we have something called as MROM, that is masked ROM, PROM. Okay, uh, programmable read-only memory, OTP, one-time programmable memory. This is not one-time password. So one-time programmable memory, EPROM, electrically programmable read-only memory, EPROM, so electrically erasable programmable read-only memory, flash memory, all these things. And these are all the firmwares. So the storages for holding the firmware software. Okay, and then we also learn about this random access memory. So we have something called as serial access memory, SAM, static random access memory, SRAM, so dynamic random access memory, DRAM. So here we discuss the implementation details of SRAM and DRAM. Okay, and then we have something called as NVRAM also. What is this NVRAM? Non-volatile static RAM. Okay, so these are as I say, usually RAMs are volatile. So when there is no power supply, so they forget everything. Okay, so but this NVRAM, so is a special case. So even it's going to remember the data after the power is what turned off. So and then we also understand the factors that needs to be considered while selecting the memory. So we have these many types of memory for storing the firmware and these many types of memory for storing the dynamic data. Now which memory to choose? So again there are factors so which you should look in while choosing the memory. And then we also understand the role of sensors and actuators and how these sensors and actuators are interfaced to the embedded system, how they are connected to the embedded system. Okay, and so still it continues. So then, so after understanding all these various types of memories and what are the factors that you should consider while selecting the memory for the embedded system, and after understanding how the sensors and actuators, all these things are connected to the embedded system. So we go for interfacing, learn how to interface an LED, light emitting diode. Say I want to connect a light emitting diode to the microcontroller. How do I interface a light emitting diode with the micro? Say I want to write my own program. So I want to make my LED go on and off as I'm writing the program. So I want to make my LED blink for every 1 second. What happens? So it blinks for a second and goes off. The next second it blinks. So I want to make my LED on for 10 seconds, and after 10 seconds I want to make my LED go off for 3 seconds. So 10 seconds it keeps glowing, and after that 3 seconds it goes off, and again next 10 seconds it goes on off, something like this. Now all these things you can do. So for you to write a program, correct, and make LED glow as per the instructions you are written in the program, what the first thing that you got to do is you should know how to interface an LED with the microcontroller. So that is what you'll learn. So not only just an LED interfacing an LED to the microcontroller, you'll also understand how to connect a 7-segment LED. So I guess you people know the 7-segment LED. So in the previous semester when you're working on the ECLD lab, so I guess you people might have seen the 7-segment LED. Even if you don't have the knowledge on the 7-segment LED, don't worry, I'll be showing you. Okay, so because 7 segments will be there inside that. Okay, so 7-segment LED display, how to interface. So not only the 7-segment display, buzzer, which is a device which emits the audible sound. Okay, sometimes they beep, so some audible sound, some kind of audible sound they emit. Okay, so how do I interface the buzzer to the microcontroller? How do I interface a stepper motor to the microcontroller? So not only stepper motor, one more thing is missing here. You'll also learn how to interface a DC motor to the uh, microcontroller, then how to interface the relays, how to interface a keyboard or a keypad. Okay, so that will also you'll learn. So a small keypad, how do I interface it to the microcontroller, and how can I go for keying in some values from the keypad? Now how to connect a push button. So I guess you people have seen the push button. So what is this push? No, not it is not the normal switches which you see on the electrical switches. So push button is little different. So if I push it, okay, the button gets pressed, and if I take out my finger, it comes back to the original position. That is what is called as a push button. Now, and this push buttons are generally used for sending the interrupts to the processor. So, and again, you'll also learn how to interface the push button switches with a microcontroller. Okay. Now, I said you're going to learn how to interface all these things with the microcontroller. Now, for interfacing, now can I take an LED and directly connect it to the microcontroller? Not possible. Now, for interfacing all these devices with the microcontroller, you require another interface device called as 8255 PPI. So 8255 is the IC number, and PPI stands for Programmable Peripheral Interface. Okay, so it's an interface device. Now I got to take an LED. I got to connect this LED with my 8255, and this 8255 in turn is connected to the microcontroller. So direct interfacing of this LED or 7-segment display, or the keyboard, or the stepper motor, or the DC motor, or the buzzer, or the push button directly to the microcontroller is not possible. So between the device, so all these devices which I mentioned, and the microcontroller, there is an interfacing device called as 8255. 8255 is a programmable peripheral interface device. Now, why it is called as programmable peripheral interface device? So because it is possible for you to program this 8255 and choose the ports required for you. Say I want to interface LED. Now to interface LED with the microcontroller, you got to decide the port. Now which port I have to connect, where I have to connect. Okay, so 8255 normally comes with 3 ports: port A, port B, and port C. Now using which port I need to connect LED to the microcontroller. Okay, and so whether I need to make port A as input port or as output port, or correct, no, both input as well as output, all these things can be programmed and controlled. Okay, say port A, port B, and port C, these are the 3 ports which are available within 8255. So I want to make all the 3 ports as output port. Yes, you can do it. All the 3 ports as input port. Yes, you can do it. All the 3, say port A, I want to make it as input port, port B, I want to make it as output port. Yes, you can do that. How? By programming 8255. Now, how to program 8255? There is a register. So 8255 has a register called as control word register. Using that register, you can go for programming. So people are understanding?
Yes, sir.
So all these things we understand there in detail. So one example I can give you. Say to make the microcontroller operate in the Zazzle state. What you got to do? Answer me. Answer this question. Now I want to make microcontroller operate in this Zazzle state, and all of you know what is a Zazzle state is. What is that I got to do? Yes. So if I want to make microcontroller operate in this Zazzle state, that is 8-bit state, what is that I got to do?
So set both thumb and arm to 1.
No, for ARM you don't have the bit result. So there are only 2 bits, J bit and T bit. Yes or no?
Okay, sir. Yes, sir.
J bit is there and T bit is there. There is no bit name with the name ARM, ARM, or there is no bit A. So you have only 2 bits. So that is J bit and T bit. T bit is the which bit it is? 6th bit. Sorry, 5th bit. 5th bit is the T bit, and 24th bit is the J bit. So from which register? They are from which register? In which registers are they? The thumb bit and J bit, in which register are they? What is the name of the register?
CPSR.
CPSR. Current program status register. Now, if you want to make the microcontroller operate either in the thumb state or in the Jezzel state, correct, or in the ARM state, what you got to do? You got to program the CPSR. So if I ask you, yeah, make microcontroller operate in the thumb state, what is that you'll do? You'll make this as you'll access the CPSR register. Inside the CPSR register, the 24th bit, which is the bit of the Jezzel state, you'll make it as 0, and the 5th bit will make it as 1. Hope people are understanding.
Yes, sir.
Now to make 24th bit 0 and 5th bit 1, do you need to write a program? Do you need to write an instruction? Without writing instruction, can you do this?
No, sir.
Not possible. Okay. Now, so you can program CPSR register and you can change the state of the microcontroller. Similarly, by programming and are using the control word register, it is also possible to program 8255. So the ports which are available within 8255, port A, port B, and port C, it is possible. So, but in LPC 2148, we have something called as port 0, port 1, and port 2. We'll understand all those things. Now you can go for programming there. Okay, so program by using the control word register and make the ports operate either as input port or as output port. All these things can be done. Learn about the data communication interfaces. So this is what I mentioned. So we understand. So both two things here. When I say communication interfaces, so there is the communication interfaces for supporting the communication within the embedded system, and communication interfaces for supporting the communication between the embedded systems. Now within the embedded system, we have something called as, these are all the communication interfaces for supporting the communication within the embedded system, for making various components which are within the embedded systems to communicate. So we have I2C bus. So generally we call it as I square C bus. So I square C, okay, I square C bus. So serial peripheral interface, UART, universal asynchronous receiver and transmitter. So this is another form of communication interfaces for making the components within the embedded system to communicate. One wire is there, parallel bus. All these things we understand in detail. And then, so for making your embedded system communicate with the external world or other embedded system, we go for using the communication interfaces like this. So these are all the wired communication interfaces. So RS-232C, RS-485, parallel port, USB, and these are all the wireless communication modules. Okay, and we also understand the embedded firmware and its role in the embedded system. Okay, and so after this, we also look into the reset circuit. Okay, and then burnout protection. Brownout protection circuit. Now, so this brownout protection circuit is something like a fuse for the embedded system. So I want to protect my embedded system from the damages. Okay, so either it could be because of an high voltage. Okay, so normally all embedded system they take +5 volt. +5 is the operating voltage. So in case if there is an heavy voltage, so always you can protect that embedded system by using something called as brownout protection circuit, and there is oscillator circuit also, oscillator circuit or oscillator unit. So as I was mentioning, for a processor or a microcontroller to do any job, you got to supply the clock pulses. Okay, so you need to supply the clock pulses or the clock cycles, but the processor or microcontroller doesn't have the ability to automatically generate the clock pulses on their own. So this separates circuit called as oscillator circuit or oscillator unit, which is having a small unit called as quartz crystal, is responsible for satisfying all the clocking requirement of the processor or the microcontroller. Then we understand how real-time clock is implemented, and there is something called as watchdog timers also. Okay, so these are all few things that we are going to understand in this chapter 2 of module 3. Okay, and from here the real discussion on all these things starts. So we'll stop at this point, and tomorrow afternoon session I'll be going with the lab. Okay, so today I'm going to explain you in the afternoon session, so don't miss that, please. All of you, please be present from 3 to the 3 to 4 class. So because I'm going to explain the very important thing. So if you miss today's class, so then everything will become difficult for you. So it becomes very difficult for you to understand the remaining programs of part B. So for understanding all the programs of part B, today's afternoon class, that is 3 to 4, is very important, because there I'm going to teach you, okay, LPC 2148 ports and port handling registers. So this is the basic. Without knowing this, you cannot do any program in part B. So my sincere advice is, please do be present for the class 3 to 4. So I don't want even a single person to miss that class 3 to 4. Okay, so we'll stop at this point. So if you have any queries or doubts, please feel free to discuss with me. So meantime, I'll be taking the attendance.